All right, the next part of A is for atom is molar mass. This unit is almost entirely mass. Lousy math. Oh. Yeah, I know, right? So we're going to be calculating average atomic mass, and then we're going to be converting between a mole, which is a unit that you can't use in real life, but that's what atoms use, to a gram, which we can use in real life, but atoms can't. So a gram is a unit that we made up that nature doesn't know anything about. A mole or an atom are units that nature uses, but we can't use. So we're going to convert between the two to go from a unit that nature uses to a unit that we use. Okay, so a quick review. When you look at an element on the periodic table, you see its name, and you see its atomic number, and we remind ourselves from last unit that the atomic number is the number of protons. The atomic number is the number of protons. So oxygen is atomic number 8, so it has 8 protons. 8. Now when you look at the symbol, sometimes the symbol is in Latin. So iron is Fe, because the Latin name for iron is spurus. If an atom was discovered really long time ago, it probably has a Latin name. Sometimes we keep that Latin name, and sometimes we Englishify it. If we Englishify it, then the symbol will not necessarily match the name, like iron, and copper, and potassium, and sodium. So if we Englishify the name, then our name is different than the Latin name, so the symbols don't match the name. That's just the way it works. Okay, now here's the crazy thing about elements in the periodic table. Oxygen has 8 protons. It can have 7, 8, or 9 neutrons. But the mass that's on your periodic table is not a whole number. I'll say this again. The mass on your periodic table is not a whole number. If you look at the wall, you see oxygen is pretty close to 16, but not exactly 16. And carbon is pretty close to 12, but not exactly 12. And the reason that is because the atomic mass is not shown. The atomic mass is a whole number. We don't show it on the periodic table. Instead, we show something else. What do we show on the periodic table? Anyone have a guess?
Like an average or something.
Exactly! It's an average. It's called the molar mass. And it is a weighted average of all the isotopes that exist on our planet at the time we write the periodic table.
Does that mean the periodic table is changing?
Yes, it does. The periodic table is constantly being updated as we bomb things with nuclear bombs, or as rocks decay, or as anything else goes on. As there are nuclear reactions, there is a different proportion of different isotopes in the world. So we have to keep updating the periodic table to keep up with those changes. There were a lot of changes in the 50s because we were dropping bombs left and right. And that was radically changing the abundance of various isotopes on the planet. Every time a meteor hits, every time there's any kind of big event, we have to go back and figure out what the new abundances are. So, the molar mass is a weighted average of all the isotopes on the planet.
So, why wouldn't it be the same for every element?
I'm not sure what you mean.
Like, if it's for all of them, then how come
3% of all the oxygen is oxygen 16. 10% of all the oxygen is oxygen 15. 18% of all the oxygen, you get the idea. And then someone nukes a city. Lots of radioactive particles launch out into the atmosphere, into the ground. Everything changes. Now, instead of it being 20%, it's 25%. So that weighting of how much is each isotope changes. Now, what do I mean by weighted average? It's not a simple average. You don't just add them all up and divide by the number you have. Where do you use a weighted average? Everybody does it. GPA, exactly. GPA, exactly. Your GPA takes the grade point multiplied by your number of credits. Or when you do your semester exam, that's 20% of your grade. Each quarter is 40% of your grade, and you get a weighted average of quarter 1, quarter 2, and your semester exam. That is a weighted average. Similarly, we do a weighted average to find the molar mass. We take the weight of the isotope, and we multiply it by its abundance. Would you like to see what that looks like?
No, I'm done here, thank you. Rain, turn me off.
Okay, this is how it works. It's a weighted average. All weighted averages work the same way. Just like your GPA, you take your score for the first quarter, add it to the score for the second quarter, and then add it to the score for the semester exam. You take your first quarter, you multiply it by 40%. You add your second quarter, you multiply it by 40%. You take your semester exam, you multiply it by 20%. You add those three chunks up together, and that's your final score for the semester. Similarly, you take the weight of your isotopes. So carbon is 11, 12, 13, or 14. So take isotope number 1. The weight of the isotope multiplied by the relative abundance. So maybe it's 11 times 30%. Take isotope 2, multiply its relative abundance by its weight. Maybe 12 by 80% or something. And then you add them all together. So, the good news is every molar mass calculation is the same. It's all abundance times weight plus abundance times weight plus abundance times weight. So the good news is the isotope mass is almost always going to be given to you in a whole number, and the abundance will almost always be given to you in a percentage. The tricky thing is this. Percentages, like 80%, you don't punch in 80 times. What do you punch in? 0.80 times. And sometimes it gives you a crazy percent, like 1%. So 1% becomes 0.01. But what if it's 0.5%? These are the ones exactly, 0.005. These are the ones that get everybody. It's 0.005. Watch out for that decimal. That's what gets everybody. If you have a decimal percent, you still move the decimal to plate. Hopefully that looks familiar. Give me a thumbs up if you know what I'm talking about. Excellent. Okay. Are we ready to do some practice molar mass calculations?
Not really.
No. Okay. We'll wait until you're ready. How about now? How about now? 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 How about now? Okay. You will need your calculator for this. So isotope element Wagnerium are found below. Wagnerium 18 has an abundance of 25%. Wagnerium 19 has an abundance of 60%, and Wagnerium 20 has an abundance of 15%. What is the average atomic mass, also known as molar mass, of naturally occurring Wagnerium? And again, calculator, pretty much necessary here. The relative abundance is 25% of the 18 isotope. The relative abundance is 60% of the 19 isotope. And the 20 isotope has an abundance of 15%. Yes. Yep.
What units would be used for?
It's going to be in units of grams per mole.
So gram/mol.
Wait, hold on, I have a question.
Yes. The whole number. Yeah. The 18.0. Using the weighted average. So you take the 18 multiplied by 0.25.
Yeah.
Add that to 19 multiplied
Yeah,
by
I
that.
did that.
Then you add 3.
Yeah, all three, and then you divide it by.
No.
Oh, you just add one.
Yep, you add them all 3. You don't divide it by 3 at the end. Now obviously when you do an average, your number should be larger than the smallest number and smaller than the larger number. It's going to fall somewhere inside of 18 and 20.
So you just add these.
Yeah, add the chunks.
Well,
Add up the chunks.
do this stuff. Where you
It's given to us at 25%.
So then you just write that as grams/mol.
Yes, grams/moles. So here's your math if you're still struggling with it. It's 18 times 0.25 because 18 for the weight and 0.25 for the abundance. 19 times 0.60, 19 for the weight, 0.60 for the abundance. And 20 times 0.15, 20 for the weight and 0.15 for the abundance. Sounds about right. Maybe it was a no name. This is the atomic. This is A1. There might have been an A2 worksheet too. Either that or someone's just scared of you and they just put it in the box. Okay. Give me some time to empty out the box later on today.
Hey, I'll give you 18.9.
I used that math right there.
Oh, okay.
18 times 0.25 plus 19 times 0.6 plus 20 times 0.15. Now, if you all want to do it in one big math equation, you can. If you want to do it in 3 pieces, then add the pieces together, you'll get the exact same answer. Other questions about this basic structure? Yeah.
Can I go back to that thing? Because I think put down was like below or not
That?
average. Yeah.
For what?
How about this one? Gallium. So now this is a word exercise, but the math doesn't change. The 4 isotopes of gallium are 34 at 12%, 35 at 25%, and 36 at 33%. And then the 4th isotope, the 4th this time, 37 at 30%. So on your own, if you would, calculate the average atomic mass of gallium.
Do it.
Yep. Okay, so are we ready to move on? I use that math. 34 times 0.12 plus 35 plus 0.25 plus 36 times 0.33 plus 37 times 0.30. And I got 35.8.
Yeah.
Okay.
Ausgezeichnet, as they say in German. Outstanding. Literally. Outstanding. Actually, it's outbeing, but close enough. Okay, any questions about this system before we move on? Okay, well that's fun math. How about another math?
Oh, crap.
I like it.
I hate my life. So I'm not rat.
It's a mole.
I'm a rat.
It's a mole with a drill. I'm pretty sure it's supposed to be a drill.
There we go.
Well, it's a cartoon.
That's a turkey.
All right, ladies and gentlemen.
Being held by a rat.
Now, I wasn't there when they named this number. They just did. I don't know why they called it the mole. They just did. But it's a very, very, very important number.
Oh, God.
If you're in the front row, it's right up there. 6.022 times 10 to the 23rd. This is known as Avogadro's number.
Are you looking at avocado?
Close enough. Okay. So, Avogadro's number is the number of things in a mole. And chemists know this number by heart. Just like you, if I was to ask you to bring me a half a dozen eggs, how many would you bring me? 6. If I was to ask you to bring me a dozen donuts, how many would you bring me?
13. Well, I'd bring you 0.
So you'd be like, they're my donuts. No, just a normal dozen. 12.
13, one for me.
Only if you make
I
it.
say it's
It's you get the baker's dozen is you get 12, the baker gets 1. That's why they call it a baker's dozen. You don't get 13. He takes a dozen, a 1 for himself in the dozen. But anyway, but it's a 12. You know how many these things are. You know how many these things are. Just like you know there are 3 feet in a yard. Just like you know that there are 100 yards in a football field, plus the end zones. Okay? Chemists know that a mole is 6.02 times 10 to the 23rd things. It's just like a dozen. It allows us to convert between something we can use and something we can't use.
So why do they call it a mole? You know why?
Like I said, I have no idea.
There's 7 billion people on Earth.
Closer to 7.1 billion now, but yes.
They start running out.
Yeah.
Oh,
Yep.
Wow, okay.
yeah, you heard that.
bunch of things that we can't use. We cannot use atoms. They're simply too small. What we can use are grams. Now, in this vial of copper, this vial of copper weighs 63.5 grams. There are 1 mole of copper atoms in this vial. How do I know there is a mole of copper atoms in this vial? I did the math. Now, if you look at the periodic table for copper, copper has a molar mass, I'm trying my best to keep the dot in there, of 63.546 grams per mole. That means if you have 63.5 grams, you have 1 mole of copper atoms. I'll say it again. The periodic table gives us the molar mass. The molar mass of copper is 63.5 grams per mole, which means if I have 63.5 grams, I have 1 mole. If I want 1 mole, how much do I weigh out? 63.5, which is what I did. I put the vial on my balance, and I kept adding pennies, or fractions of pennies, until I had 63.5 grams. That was 1 mole. And that means, in this vial, I have 6.02 times 10 to the 23rd atoms.
What?
If I have a mole, I have 6.02 times 10 to the 23rd atoms. Now, that 6.02 times 10 to the 23rd, anything. It could be atoms of copper. It could be atoms of arsenic. It could be atoms of helium. It could be puppies. It's 6.02 times 10 to the 23rd, anything. But here's the cool thing. Because of how much each copper weighs, when I have that number of copper, I have 63.5 grams. Okay. Nod your heads, this is starting to come into focus. Question mark.
So if you would have like a double of 63.5, you would have 2 moles, which would be like
12. Yep. So Weston asked a really good question. He said if you had twice as much, so if I had 126, if I had 126 grams, then I would have 2 moles, which means I would have 12 times 10 to the 23rd. Make sense? So here's copper. Here's table sugar. Now, table sugar weighs 342 grams per mole. It's a lot more. No, I glued the lid on. Otherwise, the ants would be all over it. Here's table salt, sodium chloride. Table salt is 48.5, a little less, but still a mole. There's the same number of atoms in this table salt as there are in this table sugar as there are in this vial of old pennies, because they're all 1 mole. Would you want a mole of pennies? If you had a mole of pennies, where would you keep them? A mole of pennies spread out over the entire earth. How deep would it be?
Like 6 miles.
Let's say you spread it out over the entire earth and somehow floated on the ocean. If you had a mole of pennies, 6.02 times 10 to the 23rd pennies,
Put it in a bag.
it would be about a mile deep.
Wait, didn't you just say that?
Mile deep of pennies. That's a mole of atoms.
Oh, not a mole.
But if you had a mole of pennies, mile deep.
You too.
If you had a mole of dollars, probably about a half a mile deep. Where would you keep them all?
Do I go for the
In my pocket.
There we go. I say, I'm all $100 bills. I'm the richest person in the world.
Okay. Does this make sense so far?
Yes.
The mole is a really big number, and it's how we relate. It's how we relate things we can use, atoms, to things we can't use. Sorry, the things we can't use, 3 moles, all you would do is you'd multiply your 6.02 times 10 to the 23rd by 3. What would you do to the periodic table? You take the molar mass and you do what? Multiply by 3. So if I said, I need 3 moles of copper, you're like, okay, 3.5 times 3. That's how much I need to weigh out. And that's how many atoms I would have. So how many molecules is half a mole? 3 times 10 to the 23rd. How much is 2 moles? 12 times 10 to the 23rd. Does this idea make sense?
Yeah.
Okay. Oh, you weren't ready? Okay, sorry.
Wait. So,
Yes, sir.
you said if you were doing 1/2, you would do 3 times 10 to 23rd, but that's not half, because it's like, it has a decimal.
Still half-ish. Half enough.
Would it work if you just multiplied it by 0.5?
Yep.
Okay.
Okay, so is this kind of making a little bit of sense? This crazy idea about the moles and such? Avogadro's number. Okay, so again, some lingo. Molar mass is what you find on the periodic table. By the way, in case you're wondering, I'm not going to give you any homework because I'm just going to talk until the bell rings. We have no, you probably figured out, if I haven't given you something by now, you're not getting any homework. So the molar mass is the thing that we use. It's all we can use. I can't weigh out individual isotopes, but I can weigh out the molar mass of isotopes. So the molar mass is measured in grams per mole. It is, on the periodic table, the number of grams in 1 mole. You can read palladium, right? What's palladium's molar mass? 106.42. If I say, go in the back and weigh out 1 mole of palladium, how much are you coming back with?
106.42.
Exactly. And you would have 6 times 10 to the 23rd atoms. If I said, this experiment requires 1 mole of sodium, you're going to say, I'm going to need how much sodium?
22.990.
Right, 22.990 grams. I can't weigh out atoms. I can't even weigh out moles. What I can weigh out is grams. Okay, so the average atomic mass of carbon is 12.01. What's the mass of 1 mole of carbon? Anyone?
12.01.
12.01.
Right.
What is the molar mass of copper?
63.546.
Excellent, 63.546. And what is the molar mass of nitrogen? This one's tricky.
Is that a 9? 19
On the periodic table, it's 14.000. So it's 14 on the periodic table. But remember Brinkelhoff? Brinkelhoff tells us the diatomic molecules. Brinkelhoff tells us that nitrogen is a diatomic molecule. It is never found alone. So nitrogen wouldn't be 14, it would be 28. 14 times 2. So nitrogen would be 28. 14 times 2. And this one you can do on your own if you have enough time. Using your periodic table, what is the molar mass of CO2? CO2. That stuff you're breathing out in small quantities as you exhale.
So there's 2 oxygens, we have those 8 carbons.
Yes. Add 1 carbon to 2 oxygens. Yeah, I think you're out of here at 39 for the assembly.
Oh, I have this.
We get out of.
Anyone have an answer? Only one of you has an answer? If you think it is larger than 10, raise your hand. If you think it's larger than 20, raise your hand. Larger than 30. Larger than 40. Larger than 50. 44?
I was not.